Good morning. I'm Katie Shilton. I'm a SoDa associate and an associate professor in the College of Information Studies. First, just a note, this webinar is being recorded and it will be available on the SoDa website by next week. And for those in the audience, please feel free to use the Q&A feature during the event to post your questions throughout the presentation. Then we'll have a Q&A period after the presentation. And so first I want to start by welcoming our guests, and I'm going to introduce Tracy Sweet. She's an associate professor in measurement statistics and evaluation program at the Department of Human Development and Quantitative Methodology. She completed her Ph.D. in statistics at Carnegie Mellon University and an MA in mathematics at Morgan State University. Her research focuses on methods for social network analysis with particular focus on multi-level social network models. Recent projects include network interference and missing data. She serves as the Associate Director of Research for UMCP for the Maryland Longitudinal Data System Center and currently oversees projects on applying data science and statistical methods on large-scale educational data. Finally, Dr. Sweet is committed to improving diversity in the fields of statistics and quantitative methodology. She serves on the DEI committee for her department and the Council's College on Racial Equity and Justice, and is interested in exploring how race and ethnicity is analyzed in quantitative methods. So Tracy, I will ask you to introduce your team and turn it over to you.
Thank you. Hi, everyone. I'm Tracy Sweet. I'd like to introduce the two other panelists. I just want to apologize because I don't have lengthy bios for Dr. Steiner or Dr. Yang. I wasn't sure. I didn't realize that we were going to be doing bios, so I apologize for not having long bios, but I'll introduce the other panelists kind of in order of how we'll speak. So, I will give an overview of the program, and then Dr. Ji-Sung Yang will talk about some of her research in the area of psychometrics. Dr. Yang is an associate professor also in the same program, measurement statistics and evaluation, and she's been at the University of Maryland for about 8 years. This is our 9th year we entered together. And then after that, Dr. Peter Steiner will be talking about some of his work on design and replication. And he is an associate professor also in the same program, same department. And Dr. Steiner joined the University of Maryland. It's always confusing talking in November because it's like a year and a half or 2 years ago. And then I'll kind of conclude by talking a little bit about my research in social network analysis. So thank you everyone again for joining us, and I'm gonna share my screen and get started to talk about the program. Now I don't have, okay, before I could share just the slides, but now I don't have my slides. Why don't I have my, oh, this is the wrong slides. Sorry about that. Okay. So the measurement statistics and evaluation program, we are part of the Department of Human Development and Quantitative Methodology. And I just want to briefly talk about what measurement statistics and evaluation are. We often think of them as components of basically quantitative methods that are commonly used in social science research. So by measurement, I really am talking about how we measure things. So in other fields, it's pretty simple to think about measurement. I can use a thermometer to take my temperature. I can use a scale to measure my weight. But in the social sciences, we have different types of constructs or things that we're interested in measuring. We might be interested in measuring cognitive ability, for example, and we would use an assessment for that. We might be interested in measuring depression, and we might use survey items for that. And so the field of measurement is really focused on how do we develop these instruments? How do we select which items should belong in a test or an assessment? How long should these assessments or surveys be? And how do we end up actually then measuring the thing that we want to measure, like cognitive ability or depression? Another part of the field has to do with then applying these mathematical models to actually come up with these depression or cognitive ability scores, and then incorporating that information into more standard models, such as statistical models like regression, for example. If I don't actually know that I'm measuring depression or cognitive ability perfectly based on the items that I'm using, I need to account for that in the mathematical models that I'm using. And then finally, a third component of the field of measurement is about the development and evaluation of methods and models for measurement. I'm not going to talk as much about statistics. I think a lot of the audience is probably pretty familiar with the field of statistics. Statistics tends to focus on things like research design, data collection and analysis. That includes things like sampling frameworks, also data visualization and exploratory analysis, as well as the statistical inference, such as regression and things like that. And then, of course, there's also the focus on methodological research, such as the development of methods and models for statistics. Finally, the field of evaluation is kind of a blending of measurement statistics and a specific content area. The goal is to be able to assess whether a program or a policy, whether it's effective or what the outcome is, and we would incorporate all three of those components, measurement, statistics, and content area knowledge, to be able to evaluate a particular program or policy. So as I mentioned before, our program is housed within the College of Education and within the Department of Human Development and Quantitative Methodology. The name of our program is Measurement, Statistics, and Evaluation, but our program in other universities might have names like Quantitative Methodology, Quantitative Research Methods, or even Quantitative Psychology. Just to give an example of some of the courses that we offer, we do offer introductory courses, and then the next block talks about core courses. These are kind of your first year master's level type classes. We offer courses in applied measurement, general linear models, as well as causal inference. And then for our more advanced courses, we offer courses in measurement and psychometrics. Dr. Yang will talk more about psychometrics if that term is unfamiliar to you. So things like instrumentation or how you write items, exploratory latent and composite variable methods. That course includes things like factor analysis, if maybe you've heard that. Modern measurement theory, that's a course about item response theory, if that term is something that you've heard before. Structural equation modeling, as well as a series of other courses about psychometrics and assessment, as well as some non-parametric versions of item response theory and structural equation modeling. We also offer courses in research design and statistics as well. So we offer a lot of modeling courses. Our main, I guess, research design course right now is called Graphical Models that Dr. Steiner teaches. We have courses on multi-level modeling, longitudinal modeling, mixture modeling, social network modeling. We also offer a course on kind of statistical consulting. There's a class on simulation. So how do you run and execute simulations, as well as Bayesian inference and analysis. Okay, so just to, I don't want to do a direct compare and contrast, but just to talk a little bit about quantitative methods programs compared to maybe more a standard data science program. Quantitative methods programs tend to emphasize measurement and assessment. So our students will take a lot of courses on psychometric modeling, on measurement, assessment. There tends to be a emphasis on research design and experimentation. There's an emphasis on statistical model, parameter estimation, and interpretation, as opposed to prediction, for example, like in machine learning. There's also an emphasis on causal inference. The research that's conducted is largely focused on methodology, so developing and evaluating new methods and models. And a lot of this work is done using simulation-based approaches. The things that I think are most similar to data science programs are the types of research questions we're trying to answer. So really complex research questions in various fields, as well as the emphasis on programming languages such as R and Python and the use of computation. Okay, so we offer a master's degree, a master's of science degree, as well as a PhD degree. We actually have a 5th year bachelor's of science, master's of science program for undergraduate students, as well as a regular master's program. We also offer a certificate, and many students at the University of Maryland who are enrolled in other PhD programs will choose to earn a certificate or even a master's degree in our program. Our PhD degree really trains students for methodological research. And so many of our graduates will go off to positions in academia or leadership positions as statisticians or psychometricians. So just to give an example of some recent job placements, faculty positions at Arizona State, Minnesota, Champlain, Georgetown, George Washington, University of Alabama. But I also want to highlight some of the job titles and industries that our master's and PhD graduates currently have. So just in the past couple of years, we have people working for the Applied Research Laboratory for Intelligence, data analyst at Drexel, statistician at RTI, a director of examinations at the CFP board. We have someone that's here at University of Maryland as the assistant director for assessment and research, as well as a researcher at Mathematica. And then you can see for the PhD graduates, they tend to be in more senior positions, so senior psychometrician positions. There's a psychometrician position at Duolingo, senior researchers at American Institutes for Research. 2 of our recent graduates are currently working as product analysts, basically data scientists at Google. We have 1 recent graduate employed as a mathematical statistician at the FDA, as well as another data scientist at C.H. Robinson. So these jobs are really similar, I think, other than maybe the psychometrician jobs, to folks who are graduating with PhDs in statistics or data science. So the careers that our graduates choose tend to have a lot of overlap with data science. Just to hear pictures of our students. It's not all of our students. These are the students that emailed pictures over the time that they've been with us. But they come from a variety of undergraduate programs, and some of them from undergraduate programs here at Maryland. We typically get PhD students from graduate programs in, excuse me, education, statistics, or psychology. And then a lot of our students also are currently in careers in education, assessment, or data analysis. Finally, I just want to talk really briefly about our faculty, because Dr. Yang and Dr. Steiner will be sharing some of their research with you today. But just we can kind of think of all of the faculty doing research in kind of one of 4 areas: psychometrics, latent variable models, research, study design, or causal inference, or a lot of them will do research in more than one category. So that is it for me, and I'm going to turn it over to Dr. Yang to talk about psychometrics research.
Thank you, Tracy. So let me just share my screen here. Let's see. All right, hi everyone. My name is Jisung Yang, and just to introduce by the Dr. Sweet. So I'm going to talk about a brief introduction of the psychometrics and what my research is about these days. And I made this title of this talk is Developments in Latent Variable Models, Measuring from Intelligence to Gender. So the psychometrics is, although the name is interesting, always there's a funny thing, when you have a, conferences and what kind of, people outside of society ask, like, what kind of, conferences you guys doing? And we are psychometricians, and they were like, psycho what? That's usually the the response that we get from the world. But psychometrics is the discipline to understand and solve unique challenges that are involved in the measurement of any, psychological, social, educational attributes that we call. So it's very related with a lot of the item analysis that you might do quickly, and the definition of reliability, validity, and fairness of the test scores, and how we can actually provide empirical evidence about this reliability, validity, and fairness of the test scores. And those are the most like the major topics that psychometricians are studying about. And this test theory that psychometricians build upon is generally applicable to a lot of measurement situations in any field. So that's why we see a lot of applications of those. So starting from the intelligence in psychology and all those high stake standardized tests that you have once taken at least once in your life before, and personality tests that you might encounter over the net, or a lot of the political polls, or a lot of assessment that were involved in, at the level of international, national level, state level, classroom level. Those are all built up on this, test theory can be applicable there. And then consumer satisfaction survey that a lot of, the Google, Amazon are doing. And in health field, health research field, the patient-reported outcomes measurement information systems that FDA or a lot of the NIH, the people are using, and those are all, the based upon what they claim they're just state-of-art psychometrics indeed. So I'm gonna starting from the very classic example of the measuring the intelligence problem that Spearman brought in 1904. So you can see that he had this correlation matrix of the some of those tests that they used back then as a mental test. So there's a classics, French, English, and mathematics, and it's a discrimination of the pitch that people can discriminate properly the pitch, and the music. And then we have this correlation matrix, and there's a theory, and this is related with the question that was just imposed for Spearman's cases. He had a theory called general intelligence. So any new, like these two tests of the mental ability will be correlated somehow because both depend on the general factor G. And pairs of tests that has a higher correlation are characterized by the greater influence of the G. So without this modern statistics, he managed to estimate the influence of G on the test from the correlation matrices. And these are the first column that you see here, the correlation with the general intelligence for each activities. And you can see the pitch discrimination is a little low, music is a little low based on his theory and his data. And then also he was able to calculate, how much variability in classics, French or English can be explained by the G factor. So there's a 84% of the variance in the French can be explained by G factor or general intelligence. So that's how he managed it back then, 2 centuries ago. And in a modern terminology, this correlation with the general factor G is considered as a factor loadings in vector analysis, and this variance explained by the G factor is also called communality in the modern terms. So what he had in mind back then is expressed in a modern, the modeling, the statistical model equation here is the observed variable can be explained by this factor, the latent factor or the common factor that is not observed that he called as a G factor directly. And that is explained by that. And the slopes, regression slopes that you can see lambdas here are the factor loadings. And then there's also unexplained part that we call the unique factor. So any observed response or observed score can be explained by this common factor and this unique factor. So that's what he had in mind back then. So it's like, you can imagine this is a simple linear regression in a manifest variable or observed variable onto the common factor, or sometimes we call the latent variable. And this communality is just simply becomes the R squared that we talked about in simple linear regression model term. But just like the modern psychologist, the Thurston 1947, and he did not endorsed the notion of the general intelligence, one-factor theory. And instead, he proposed the multiple factor analysis, and which is known to be the common factor analysis and used a lot in this modern measurement theory world. And that becomes just the extension of the simple linear model, simple linear regression is extended now toward the multi-factor model, so multiple linear regression models here. And this model typically has assumptions on this, and this is called, in a modern term, linear normal factor analysis. And we say the common factors are independent from the unique factors, and unique factors are independent each other, and the unique factors have zero means. And also for the maximum likelihood estimation, it is typically assumed the normal distribution of this unique factor and the common factor. So the latent variables are typically normally distributed in a lot of applications. However, these assumptions are not always reasonable to make. And here is an example of the study that I involved in together. So this is about the self-report of gender. And I'll just briefly describe about this context. So recent decade, you have seen a lot of different terms of the gender identity terms and descriptions. And here are some examples that I provided here in the parentheses. And some of them might be familiar to you, and some of might be just still new terms to you. And the goal of this project was to create a self-communication tool that allows for the characterization of the genders, even for the people who are not really have access to this sophisticated gender terminology that is, still being, growing and being developed. So what we end up with eventually is a multidimensional gender characterization tool for the gender diverse group or the cisgender youth and adults. So basically this gender diverse and cisgender youth and adults are the population that we are targeting to use this measure. And to be able to do that, so we also have to expand our, the linear factor model toward a certain degrees here. So the items are, so here's one example item here that I can brought here. So if I could choose, I would be glad to have a female body. And then the responses that usually, typical Likert scale that is not continuous. And you can see the never true, sometimes true, often true, always true. So those 4 response options are given, and that's ordinal responses. So the linear normal factor analysis that I presented before, and that was used for the Thurston's or the Pierce, the Spearman, is now extended toward what we call item factor analysis, or sometimes called the item response theory model. So now we are connecting or the relating to each response category 0, 1, 2, 3. So the probability of choosing the category is connected to this latent variable on X side. So you can see that if this item is actually measuring the female body side, so if the femaleness score is higher, then highly likely there's a higher probability of the choosing the higher categories. And that's what you can see here. And by the weighting of this summation of this item characteristics curve, then we can see this expected score. So if a person is an average level of a femaleness and that person's expected score, item score on this item is about 1.5. And this is interesting because we can connect this item properties into the scale of the measure that we are trying to, the scale of the continuum of the scale that we are trying to measure, which is femaleness in this case. So we can do a lot of interesting things from here by this IRT, like, you give the more informative items, the people you're trying to measure, the people who are above the average of the people, then you're giving more items that are more discriminating up to here. So those adaptive testings that you have done in GRE type of things are all possible, thanks to this kind of the latent variable modeling or class, or I would say the IRT in this cases. So we had a data, more than 1,000 people here and average ages here. And we found that there are 2 common factors actually behind these 20 items that we end up with. This first spectrum is the maleness and femaleness spectrum. So in this spectrum, the higher score means basically more femaleness. So if you have a lower on this score, that means more maleness. And then we also saw the non-binary gender diversity dimension. And if someone has a higher score on this dimension, means the binary, less binary in self report gender. So you can imagine the people who are not characterized as a traditional, binary gender would have a higher scores on this non-binary gender diversity dimension. And analysis has been done with multidimensional, because we have multidimensions, and mixture modeling with the great responses that I provided as a graph, as the model. The reason is that because if you think about the maleness and femaleness, and a lot of people are actually, like still like in this world, like maleness and high on the maleness and lower on the high on the femaleness. So you can imagine like very bimodal distributions too. And if you study to looking at non-binary gender diversity too, it's not necessarily normally distributed, as you can see. So all those, the Gaussian distribution assumption on common factors were violated. So we had to use the different techniques called the mixture modeling. And then we also used this as a multiple group analysis to make this measure working properly or in the same way across the age group, and also inclusive for the people who have, for example, the ASD, but then also have a high level of intelligence still. So to make this inclusive and to be able to use care about this subpopulations, and with this kind of a differential item functioning test in psychometric. So this is the results that we saw. So it turned out at least the three normal mixture densities will help us to characterize this non-normal density of this two-dimensional the latent variables. And you can see the non-binary gender diversity. Many of them are below 0. So that means many of them are still like very binary gender characterizations. But then also you see that some of them are higher than 0, and these people are the ones probably also not necessarily female or not necessarily male to characterize themselves. And then we see that the people who have lower scores on the non-binary gender diversity scores are more extreme in terms of the high femaleness and lower femaleness. So lower femaleness means the maleness here. And then you can see the three-dimensional density plots on this. And then there is a differential item functioning we also found here. And this item, particular item, having hair on my face, like a beard or the mustache, would very upsetting me. And between the autistic group and allistic groups, and you can see that if the same level of femaleness is assumed, then more likely this autistic group will be bothered or not liking this, the hair on their face, given this. So we actually moved out, removed those items that have a large impact on what we call the large impact, the differential item functioning, and removed these items. And that's what we end up with 28 items. And just like this, a lot of application studies that I involved in here, like there is your validation of the grid measure, and there's also validation of the language sample analysis indexes. And here the red colors are the ones, the in progress studies with other teams that I'm involved in. And differential item functioning, whether this language sample analysis, when you do it, between the African American English speakers versus the general American English speakers, will have some different impact or something. So those are the ones that we are looking at also. And Sepha reported the ASD screening measure, or these kind of things also, not only just traditional context, but also can be used in a tablet-based adaptive testing for all the children's tasks on the social executive learnings. And there are these methodological studies that I'm involved in, try to, again, this liberate these assumptions that I described before. So under the more complex measurement conditions, and those independence assumptions are violated, cluster sampling, longitudinal item response data, and the hierarchical item factor models. So those are the ones that I involved before. And then there are also in progress studies to handle this item response model with the count response data instead of just the ordinal data, and also the group fit statistics for the multi-level item response models. And handling this non-normal latent densities can be done with multiple ways, although I applied this mixture of normals, but it can be definitely based on the semi-parametric approaches, as you can imagine. So those are the ones that I'm also involved in. And also interesting thing is the statistical inferences in this IRT applications, and it involves multi-stage estimations and how do we ensure this sound inferences, statistical inferences, and those are the topics that I am interested in working on. So Now, I hope just I answered a little bit of that theory questions here. And I know that Peter is going to answer about the question again about the theory. So I'm going to just pass this mic to Dr. Steiner here.
Okay, thank you very much, Chi-Sung. I just realized that I'm running out of power here, so I have to get the cord, and I hope I plugged it in correctly. Otherwise, I will be soon out of power. Okay, let me share my screen. Okay, I hope you can see my screen. So my research is essentially all about causal inference, and so is my teaching. So I want to give you a little bit an idea about what causal inference is about, and particularly what my research is about. And we can just start here. So my entire focus is on the foundations, research designs and analysis, everything devoted to causal inference. And one could say there are four main topics I address. First, the design and analysis of quasi-experiments. Then I also focus quite a bit on causal replication designs, which is particularly important in the times of the replication crisis. And I also do a little bit of research on factorial surveys and vignette experiments. And I'm also interested in the philosophical and conceptual aspects of causation. Before I go a little bit more into detail with regard to these four topics, I would like to talk about why I believe that research on causal inference really matters in these days. So we face one main challenge in causal inference. And it's probably best summarized by a quote from Pearl and Mackenzie's book called The Book of Why, where they say data are profoundly dumb about causal relationships. So the question is, where do we get the information from that there might be causal relationships? How is causal inference even possible if data cannot tell us anything about causal relationships? And this very nicely relates to a question we had in the Q&A section already in there. What we need is subject matter knowledge. So we need theories about the data generating processes that presumably produce the data in hand. Without subject matter theory, it's essentially impossible to draw causal conclusions. So subject matter theory is important because first, it informs the research design. And second, it's important to assess the credibility of all the causal assumptions required for drawing causal conclusions. Right, so subject matter theory is needed to decide on which variables you want to block or stratify, for instance, to reduce error variance. And it's also very helpful in implementing randomization procedures because you want to have a randomized experiment that doesn't break where people adhere to the assigned treatment status. When it's about assessing the credibility of assumptions, you probably are familiar with lots of those technical terms: unconfoundedness or ignorability assumption, common trend assumption, exogeneity, or the monotonicity assumption. And Nancy Cartwright, a philosopher, very nicely put it: no cause is in, no cause is out. So if you cannot provide subject theory that warrants a causal interpretation of your results, then you cannot draw any causal conclusions. With data alone, there is no way that you can come up with cause-effect relationship claims. So to highlight this even more, I put here two more recent quotes also in there, one from philosophy, one from economics. And it's very clear there are no explicit causal relations in data sets. So what we require is further knowledge on phenomena producing the data under consideration. Or like Cunningham says, an atheoretical approach to empiricism will simply fail. Not even big data will solve this problem. Causal inference is not solved with more data. Causal inference requires knowledge about the behavioral processes. Without them, one cannot hope to devise a credible identification strategy. So these quotes make it very clear that if we don't have strong subject matter theory, it's very hard to justify the strong causal assumptions on which our causal claims rest. However, there's no kind of a tension, because the more assumptions we make, the less credible will our conclusions be. And that's very nicely formulated what Jakmansky calls the law of decreasing credibility. The credibility of inferences decreases with the strength of the assumptions maintained. And when we do causal inference, we make a lot of assumptions, a lot of strong assumptions, okay? Knowing this, so you might better understand what my focus of research is, because I want to do research on research designs for causal inference that maintain the weakest assumptions possible. And what is particularly important in teaching is it's important that we understand the causal assumptions and the implications of their violations, because it's not sufficient to just make a technical assumption without understanding what the assumption means. We have to justify those assumptions based on subject matter theory. Okay, so when it comes to the design and analysis of quasi-experiments, I'm particularly interested in, besides of course randomized experiments, in regression discontinuity designs, in matching designs, and you have probably heard the term propensity score matching a lot before, which is heavily used. And we can also use it in inverse probability of treatment weighting. And matching designs rely on the assumption that you measure the set of covariates that is able to remove the entire confounding bias. But we also know research designs and estimators like instrumental variable estimators or gain score estimators, also called difference and differences estimators, that can deal with unobserved confounding. Right? And other class of designs or estimators come from interrupted time series designs, where we have repeated measurements over time, where we typically rely on functional form assumptions to draw causal conclusions. But all the assumptions of those designs, maybe with the exception of regression discontinuity designs, require more and stronger assumptions than a randomized experiment does. Even a randomized experiment has some quite strong assumptions built in. Okay, besides my research and interests on quasi-experimental designs, directly from this line of research, about 10 years ago, long ago, we started together with Vivian Wang from the University of Virginia looking at causal replication, which then became so very important after the replication crisis hit the medium. So what we do is we take a causal perspective in order to define what the goal of a replication is. And we define the goal of a replication as the causal quantity of interest. We have not really an interest in replicating correlational quantities. Then we also outlined all the assumptions that need to be met in order to achieve replication success. And it turns out the list of assumptions is long and strong. But just looking at those assumptions, you will immediately realize in the social sciences, you cannot expect high replication rates because the assumptions are almost truly violated because the effect generating processes that differ from site to site and they vary over time. Then we also looked at how to assess replication success. So we looked at correspondence measures in order to make more informed assessments of replication success or failure. And currently we're working on different designs of systematic replication efforts. For instance, you want to run 10, 20, 30 studies. And how do you vary systematically different factors, let's say population characteristics or setting characteristics across the studies such that you get the most information out of it. So we use your fractional or the efficient designs in order to suggest replication designs. I also do a little bit research on the design and analysis of factorial surveys, which are randomized experiments within a survey, and vignettes are short descriptions or representations of scenarios that are created by factorially combining levels of vignette characteristics. And also here we use fractional and confounded factorial designs, efficient designs, and together with the former student, we particularly looked at context effects created by the vignette sets or the order of vignettes. The analysis typically involves ANOVA or multilevel models. So finally, I'm very interested in philosophical and conceptual foundations about causation, and in particular the language or the frameworks used for defining causation, meaning what causation even means, and then how we formulate the assumptions. And coming from the Campbell, Cook, and Shadish tradition, because I worked with Tom Cook and Will Shadish for several years, I'm of course very familiar with the validity typology and the threats to validity. But I also look at the Rubin causal model and the use of potential outcomes notation, where we see here, for instance, the potential treatment outcome for a subject and the potential control outcome. These are the outcomes we would observe if a subject who gets exposed to a treatment control condition. Then we can define the individual causal effect, but only one is observed. Therefore, we have an inherent missing data problem, and the mean of those individual effects would be the average causal effect. Since the last 10 years, I also focus on structural causal models or causal graphs, also called directed acyclic graphs, where we might be interested in estimating the effect of T on Y. There might be also an indirect effect from T to C to Y. And those graphs show subject matter theory, right? And so once we do the subject matter theory, we can do an informed covariate selection in order to remove confounding bias. Okay, just I don't want to go in details here because we're running out of time, but we have different projects running here, for instance, assessing correspondence measures for replication efforts, then also clarifying the meaning of contextual effect estimates in multi-level settings. But I also regularly collaborate with applied researchers, for instance, with Eric Cameron from the University of Missouri on evaluating the Authentic Intellectual Work Initiative in Iowa. And I think I will stop here such that Tracy also has some time to talk about her research and that we have some time to do Q&As. Thank you very much.
Thanks, Peter. I'm going to just very quickly share my screen, and I'm going to talk briefly about some social network methodology research that I've been working on. So we often think of a social network as Facebook or Twitter, and that's definitely one example of a social network. We also have in real life relationships that can constitute another type of network. We have workplace relationships like co-authorship or collaboration networks. The network that you see before you is actually a network that's not constructed of people, but of schools. So the network that is pictured here is actually a school mobility network. So looking at schools that are sending and receiving students during the course of an academic year. So I'm not going to go into detail about it, but just know that networks can be more than just individuals. They also can be entities. And just like any other type of analysis, when we talk about network analysis, we can think about descriptive analysis, right? Exploratory analysis, as well as inferential analysis. So there are a number of descriptive statistics and visualization methods that one can use to kind of explore a network. There are certain structures that might be of interest. I tend to live in the world of my research focuses more on the statistical inference and prediction side of things. So I've done some work on predicting networks. So why might two people or two nodes in a network share a tie? Is it something to do about the individual person? So do we see like women tend to send more ties than men? And so somebody has a tie because one of the pair is a woman, or is there something about the dyad, the pair of people together that is important? So whether those two people are of the same race or share the same religion or ethnicity, that might be a predictor of a tie. We can flip that script altogether. Instead of thinking about predicting networks, we can actually think of networks as predictors. right? How might having a network in my study impact some outcome that I'm interested in? These are often called social influence or social diffusion, right? If I tell one person in my network something, how long is it going to take till everybody knows? And is it possible to just tell one person and have everyone know after a certain amount of time? Is it possible for me to measure that? Is it possible for me to measure the extent to which people are influenced by the people with whom they interact? So my research really focuses on social networks and interventions. In intervention, you can imagine I have 4 networks shown up here, and you can imagine maybe the 2 on the left are assigned to be in the treated condition, and the 2 on the right, those networks are assigned to be in the control condition. And let's suppose that these networks are networks of teachers in a particular school. In particular schools. So we have 4 schools and the networks of teachers within each of those schools. Intervention may change the ways in which people interact. And something that we found is that when you introduce math coaches into a school, the ways in which teachers interact around math, it changes. It's different. It's different in schools where you have coaches compared to schools where you don't have coaches. Something else that I've been working on is this idea of a network mediating the effects of an intervention, right? So the addition of math coaches in a school impacts this network structure, but then that network structure then predicts kind of the changes in belief about teaching mathematics for these teachers, right? So in schools where there are coaches, or even schools where there aren't coaches, but where we see kind of this specific network structure, we're also finding that teachers' beliefs about mathematics are changing, and changing in a more positive direction. But I'm not going to talk about either of those things anymore in detail, but I'm happy to answer emails about them or answer questions about them later. I'm going to talk about how network interactions can impact an intervention. And this goes back to some of those strong assumptions that Dr. Steiner was talking about in his presentation. And this is an idea of network interference, right? So one of the assumptions that we make when we're doing a study in which we're trying to estimate some type of causal effect or treatment effect is something called Sepha. And basically it stands for stable unit treatment value assumption. And what that means is that, you know, my treatment assignment isn't going to impact your treatment assignment, nor is it going to impact your outcome, right? So me being in the treatment condition is not going to impact your outcome. And we can kind of think about that as you know, once you've been assigned to some condition, you know, my outcome's not impacting your outcome. But we know that in a social network, this is regularly violated. We all probably know this just from personal experience. You know, you are influenced by your contacts on social media. You are influenced by the people with whom you interact regularly. So we see that this assumption is regularly violated. And I'm going to skip this picture just for the sake of time, but basically what you're seeing is that people's colors are changing as a result of the people with whom they're interacting. And so what does that mean for people who are designing studies? It means that we need to be thoughtful about the social networks that are kind of underlying these studies that we're trying to do. You know, we might go into a school and think, well, we're just going to assign this classroom to treatment and that classroom to control and collect our data. And, you know, if the assignment was randomized, we're happy with that. And we can get a nice estimate of our treatment effect. And that's kind of what you're seeing here, right? We have purple networks that might be, each box might be a classroom, and maybe the purple networks are all being assigned to treatment. The ones on the top row, the bottom row might be my control networks. But I still have within network interference. So, I mean, within condition interference. So even within this classroom, even though everyone's treated, there's still interaction happening among the students. Here's another example. So maybe this is, you know, 5th grade, for example, right? We have a lot of within condition interaction, right? Because students kind of that are in the same classroom tend to be friends, but then we also have some between classroom friends. So even though the orange students are all in the same classroom, we do have some connections across classrooms just because, students live in the same neighborhood or on the same block. And then as students get older, we might see this as even stronger, right? In high school or middle school, where students are actually mixing across classrooms, just assigning one classroom to one condition and another classroom to another condition, we still might see a lot of between condition network interference. So we have a lot of interaction across conditions. And so I'm going to just go through these really quickly. But this is some of the simulation-based work that I mentioned before that we do kind of as a program. So what you're looking at is you're looking at 100 replications of a simulation of a treatment effect, right? The true treatment effect is 0.3. You can see that right here. And you can see kind of what are the treatment effects I estimate when I have interference, which is up here, versus, when I have interference, which is down here, versus no interference. And when I have just within condition network interference, I'm not seeing any bias in my treatment effect, but I am seeing increases in the standard error. Once I have some between condition interference, and even when I have large between condition interference, I'm now seeing a bias, right? My treatment effect, even though the truth is 0.3, the majority of the time I'm actually finding a treatment effect that's smaller than that. Why is this relevant? Well, for those of us that do work in education, this is really relevant because it impacts our power. Even just having, within condition interference itself, we go from our standard 80% power down to 64% power. And as our network interference increases, you can see that the power just, plummets basically. So this impacts kind of, the work that we can do when we're doing these clustered randomized trials, as well as observational studies. I want to make sure that we have plenty of time for questions. So I'm going to skip this slide, but I am doing some work with students, and I'm happy to talk about that offline. I want to just end with this slide. So I sped through all the social network stuff, but I do want to plug our course code, which is EDMS. So for anyone who is interested in taking courses in our program, there's a causal inference course being offered in the spring. I'm teaching a social networks class in the spring, and Dr. Yang is teaching an item response theory, modern measurement theory in the spring. We are also accepting applications for our master's and PhD programs. Contact information for our program director and director of graduate studies, Dr. Yang, is here. And then I also included my email address and Dr. Steiner's email address if anybody has questions about our research. And I'm going to stop there and open it up for Q&A.
And thank you, Tracy. This is Brian Butler. I apologize for joining a little bit late. It's really interesting to learn about your work. One thing I do want to emphasize to everyone before we go into Q&A, there's the mechanics. If you have questions, put them in the Q&A section. And that's a good way to get those into the discussion. But the EDMS group has a long history of doing really interesting work in the area of social data science or social data in different contexts. And I've had multiple times over the past 5 years where I've had folks, oh, you're in Maryland. Oh, do you know about these folks doing this? And so there are people all over the world that are very familiar with the work that you guys have done. And it's great to be at the same institution, be able to work with you. So I'm going to give Anna Valentin the ability to talk because she has 2 questions. So Anna, you can go ahead and ask your question.
Yes, I am unmuting myself. Could you hear me now?
Yep. So go ahead.
Dr. Sweet, I would like to know if you had applied the network theory into system network for computing.
I haven't personally yet, but I do know that network analysis, these methods are being applied to pretty much any type of relational data. So whether that's network systems or even co-occurrences of depressive symptoms. I mean, it's being applied really broadly. So I imagine that it could be.
Okay. Thank you very much. And again, my next comment is thank you very much. It was an awesome presentation. Thank you, guys.
Thanks.
And Tracy, actually related to that, we had another question that was related to kind of measurement of networks. So do you know of examples of studies or just even advice or recommendation you give to people when they're trying to measure networks? What kind of things that they should do to make sure the network is measured well, or things they should avoid? Your work,
yeah, that's
describing of recognizing that it's there is very valuable, and kind of what can you say about the measurement of the network itself?
Sure, that's actually a project that I'm working on with two different groups in different ways. Typically, network data is collected via survey, and currently it's collected via kind of a single survey item, depending on the type of relationship you're interested in. And so I'm working with a graduate student here at Maryland, but also a group of anthropologists kind of all over the world. It's a pretty large group of us looking at kind of how you would extract a true network, given the fact that some people might lie, some people might exaggerate. So trying to take into account having additional items to use so that you can kind of identify people that exaggerate or people that are less reliable. So basically embedding a lot of the measurement principles that I would learn if I took courses with Dr. Yang into this idea of network survey construction.
And for the audience, this is something that I know in discussions of social networks online, in trace data, there are multiple good papers of bad things you can do with trace data from online systems. And one of the simple ones is assuming that just because someone is connected in a response network or a message network, that they know each other, that there's a relationship. That's a simple example, but yes, that's a really interesting kind of general measurement questions. Another question that I've gotten some that were sent directly to me. So this is for Peter. I'm just going to read the question. So do you have suggestions on how social scientists that have traditionally worked with observational data to do causal inference, say panel study, could do pre-registering? It seems like it's often not clear what effects to expect, et cetera, and the framework for registering doesn't necessarily seem to fit social science well. So kind of, do you have comments on that question or that aspect of things?
Right. So, I think there are two aspects. One is about pre-registration. The second is what you want to pre-register. I'm trying to use more and more causal graphs. When it's about observational studies, the people write down their presumed theory, how the data were generated, and then carefully think about which research design or statistical approach most likely meets the causal assumptions. And how this relates to pre-registration, I would say, is if researchers make their beliefs about the subject matter theory, the data generating process, transparent and pre-registered, everybody can discuss it and can help researchers to improve their design, because there is no point, we don't need to agree on subject matter theory, but it's clear that we show in what we believe. And causal graphs, I think, are particularly helpful. Like for IES proposals, we need to show the theory of change. The theory of change is essentially a causal graph, right? But we need more formalization, and this could directly go into pre-registering studies such that we have less degrees of freedom in doing than causal inference.
Yeah. Thank you. That makes a lot of sense. I mean, and so the last thing I wanted to say, and it was just to wrap up one time, and thank you very much for your presentations. Again, I apologize I wasn't able to be here for the whole time, but even the parts that I saw were really interesting, so I'm sure everyone benefited. Thank you everyone for joining us for I think this is the second SoDa Symposium of the year. And there's information about the next one on December 7th, where the topic will be how businesses leverage data to engage customers and employees. And this will be folks from the Smith Analytics Consortium, Wendy Moe and Wadad Soledad will be talking about the work that they're doing there. And then the last comment I would make is if you're a student or you work with undergraduates that are intrigued by this, Tracy mentioned the master's programs, DDMS, but there's also the UMD social data science major, which is going to officially be launching in, I think it's February, but if you're interested in that, certainly contact us at SoDa and we can put you in connection with that. And that's a way that you can combine the social data science and many of the measurement and methods that were talked about today with a variety of social sciences. And that's something that, while it's not in play right now, we hope someday to have an education component to that, connection with School of Education in that. But right now it's with BSOS departments and School of Public Health. So if that's of interest to you as an undergraduate, or you know students might be interested, that's something else that's available. So again, thank you, Tracy and Peter and Juzung for joining us and presenting about your work.
Great, thank you very much.
Thank you, Brian.